I know that was all very pertinent information, but let's do section or lecture 5.2, sketching the root locus. Yeah. Well, I know I was going to try to figure out how to say sketching the root locus in an Australian accent, but then I was like, I don't think I could do it.
Can you do this lecture
in an Australian? Oh, I wish I could.
Just try.
See, it's a good thing that I left the hat in Eddie Bauer.
Some high standards.
Yeah. So, it is easy to get lost in the detailed rules of manual root locus construction. The Nice textbook goes into great detail on this. In the old days, accurate root locus construction was critical. But now, it is useful only for gaining intuition for how a given system will behave given its open loop transfer function, which is extremely useful for design. So we like that. Same with the Bode plots. Having a super accurate sketch isn't necessary. It's qualitatively correct sketch that is important. And it's useful because qualitatively we can understand how our transfer functions, or our poles and our zeros, are going to affect the Bode plot in the case of Bode plots, or the root locus in the case of the root locus. So, if a detailed root locus is desired, we should use the computer tools from lecture 5.3, and then lecture 5.3, the next lecture, I'll talk about MATLAB, how to use MATLAB to do this, and it's very useful. But if we don't have the intuition, it'll be hard to design with it, which is our whole goal, is to design with it. If you're just analyzing with it, and it's like somebody gives you one, they're like, here, tell me where the closed loop poles would be for a given gain. And you're like, yeah, sure, you could use MATLAB for that. But like being able to sketch a root locus when you're doing a design problem is very important, even though you'll still use MATLAB as a tool. We will construct a procedure for sketching a root locus from the following rules. In what follows, phrases like has locus are used to describe curves in the complex plane for which the root locus is defined. That is, everywhere in the complex plane for which the root locus is defined is said to have locus. Note that some of the following rules only apply for positive gain. We talked about that last time. We're only going to consider positive gain root locus construction because that's the one that is most useful most of the time. There are very occasional situations where a negative root locus is interesting, in which case I recommend just using MATLAB, or if you want to explore in the Nice textbook how to construct a negative root locus. Okay, so here are our rules. We have 5 rules, so those are the 5. And then we're going to have a procedure that follows for how to go through and construct a root locus sketch. So we start out with the 5 rules. There are more rules if you want to get more precise with your construction, but I think that these are the 5 that get you a really nice qualitative root locus sketch without a whole lot of work. So you should be able to sketch a root locus in like a couple minutes. It shouldn't take you a long time. It should be faster than a Bode plot. Okay. All right. So rule 1: the root locus begins at open loop poles where the gain is 0 and approaches open loop zeros where the gain goes to infinity. This was shown in the last lecture to follow from the form of the closed loop transfer function. Remember, so let's just like pretend that like maybe one of you forgot what the root locus was since Monday. It's the plot of all the possible locations of closed loop poles if you've got a controller gain as your controller, right? A gain of your controller. So as you vary that gain, you see where all of the closed loop pole locations might be. So they begin, when you have the gain set to 0, they begin at the open loop poles, okay? And then they proceed to the open loop zeros. So that's a really good rule to remember, that the root locus is going to start at open loop poles and go to open loop zeros. Okay, good. Second rule is the number of branches of the root locus is equal to the number of closed loop poles. The branches are essentially created by a pole location that's swept through when you vary the gain. Okay, so you can think of there being like an Etch-a-Sketch. You guys know the Etch-a-Sketch, yeah? Yeah. Okay. It's like an Etch-a-Sketch, and you've got that little thing in there. I don't even know what it is. It's in the sand, and as you vary the gain, it's like that Etch-a-Sketch thing, like moving through and tracing out something in the sand that persists, and that's what the root locus is. So if you vary the gain, it's like moving the Etch-a-Sketch thing. Everything is related to Etch-a-Sketch, I've found. Yeah. So, okay. Good. Great. Rule 3. The root locus is symmetric about the real axis. So remember, we're sketching the root locus in the complex plane. So we've got the real axis, and then we've got the imaginary axis. Oops. And we have symmetry about the real axis for the root locus. Now, that makes sense because remember, poles and zeros also have symmetry about the real axis. Whenever there's an imaginary component that arises, you always have a complex conjugate pair, right? There's always that pair. So if you've got a pole up here, you're going to have a pole down here. If you've got a 0 up here, you're going to have a 0 down there. It's mirrored about the real axis. And that's just a mathematical requirement. It's just based on the fact that it comes from a polynomial in S. It has to have that property. Now, remember with these poles, with the root locus, you're just moving these poles around. They're sweeping them through some gain, and they're moving around like the Etch-a-Sketch as you vary that gain. And the wherever they are, like say it's at this point here, they still have to be symmetric. It's always symmetric. So the curves that you trace out with your Etch-a-Sketch also have to be symmetric. Okay. Great. So there's symmetry about the real axis. Rule 4. On the real axis, there is locus wherever an odd number of open loop zeros and poles are on the real axis to the right, and no locus elsewhere. This one sounds like a mouthful, but is the easiest one, maybe, to apply. So this is a really nice place to start our sketches, and that's what we'll do in a moment. But let's take a look at what this entails. So I'm just going to put a bunch of poles and zeros. I'm randomly deciding pole and zero here. It doesn't really matter which ones they are for this rule. Okay, so they're all on the real axis. And remember from the phase criterion. So remember the phase criterion that says that the angle of the transfer function, the sort of composite transfer function kgh, must be pi or its equivalent for us to have, when evaluated at a test point, for that test point to be on the root locus. So in order to have locus, S has to be equal to something that evaluates to pi or 3 pi or 5 pi or whatever, right? Some 2 pi mod of pi. So this is our phase criterion. And so that means, so pi is 180 degrees, right? And remember that the phase criterion, this is from the last lecture, right? From this one. The root locus must everywhere satisfy the criterion that this angle has to be equal to pi or 3 pi or 5 pi or whatever. Okay, so if we go back then to our, to here, then let's look at what happens if you have any poles or zeros off the axis. Remember, they always show up in pairs, right? So remembering that you can imagine for some test point we'll make this our test point on the axis, psi. For some test point, if you want to evaluate a transfer function at that test point, then the angle is just the sum of all the angles that the vector going from the pole to the test point added up. So the sum of all those. So if we did this, it would be that angle and that angle. So for any pair that's off the axis, these are always going to be, so if this is, say this is 45 degrees, this is going to be negative 45 degrees, right? It's always symmetric. You're always going to have, so if it was 45 degrees, then it's going to be 315 degrees. So this is 315. This is 45. And when you add 315 and 45 together, you get 360 degrees. Or in other words, there's no angle contribution from these complex conjugate pairs to any test point on the real axis. And that's what we're concerned with in this rule, what's on the real axis, right? So nothing off the axis matters. So let's look at the ones that are on the axis. If you're right of all of the poles and zeros, they all have the same zero contribution, right? The angle of the vector drawn from here to there is 0. The angle drawn from there to there is 0. The angle from there to there is 0, right? So you add up zeros, and then you add up things that just cancel each other. So if you're right of any of these poles and zeros on the real axis, you have no locus because your total angle is 0 when you add up all those angle contributions. Okay, it needs to be pi for there to be locus, right? But then as soon as if you move leftward, as soon as you skip over the first pole or 0, you're going to get a non-zero angle contribution from that one because now the angle, say your test point's in here, now your angle is pi, right? So it's either going to be plus pi or minus pi, but when you add pi or you minus pi or you subtract pi from 0, you just get pi, right? It's the same. It's equivalent. You can either go this way or you can go that way, but you get to the same point. So you're going to have locus here. And that's true until you cross over the next one, polar 0, and you're going to get another pi contribution. It's going to be either plus pi or minus pi, but it's going to take you back to 0 effectively. And it alternates. So we're going to use this. So essentially this rule means that if you're marching along the axis here, and I'm going to use a different color, and we're going to use green for the locus in this case. So if you're out here on the real axis, before you get to any polar 0, which the first one shows up here, right? That's our first pole. That's our first 0. Pole, 0. So there is no locus out here because we have 0 angle criterion. And then in here, the angle criterion is met because its angle's pi. So there would be locus. Until you get to the 0, which has a pi contribution again, which takes us back to 0 or 360. So we have none in here until we cross over another one, and then we've got locus, no locus, locus again, and then this assuming this is the last one, it goes off to infinity that way. So we've got essentially this nice rule where on the real axis, all we have to do is just start rightward of every polar 0, start out saying no locus, and then move leftward, and then as you cross over a polar 0, you switch to toggle to locus, and no locus, locus, no locus, locus, no locus, etc., until you get to the end. So it's a really easy rule to follow once you've understood the way to construct it from the angle or phase criterion. Cool. Does that make sense? That's what that wall of text effectively says, just so you know. If you want to go back and read it later, that's what it says. Oh, yeah. Okay. Okay, so rule 5. So the last rule here. Missing poles or zeros are paired with infinite zeros and poles asymptotically. So an open loop transfer function with a different number of poles and zeros is said to have missing poles or zeros. Remember, so the root locus, every branch of it starts at an open loop pole and goes to an open loop zero. But what if your open loop transfer function doesn't have the same number of poles and zeros, which is very common, in fact. So we call those missing ones. So this is because the root locus begins at open loop poles and approaches open loop zeros, but what about systems with missing open loop poles and zeros, or zeros? For these situations, the root locus begins or ends at poles or zeros at infinity, we call them. For a system with more poles than zeros, which is quite common, usually we're going to have that situation. Some poles approach zeros at infinity asymptotically. So there aren't enough finite zeros, so we're going to have these zeros at infinity that will approach asymptotically. Conversely, and rarely, for a system with more zeros than poles, which is uncommon and is called a non-causal system, some branches of the root locus begin asymptotically from poles at infinity. Okay, there's a typo there. So you notice in your text it says zeros at infinity. Actually, it should be poles at infinity. Asymptotes originate at a single real axis intercept sigma A, which can be shown to be related to the finite poles and zeros and the number of poles and zeros as well. Okay, so I'll give you an expression for that. Pardon? I'm going to give you an equation for the sigma A, for the real axis intercept. So sigma A is equal to it's sort of like an average, so it's a big fraction. The sum of over, wait, did I use I or J? I used I. Sum over I of pi of all the poles minus the sum over j of all of the zeros divided by the number of poles minus the number of zeros. So it's kind of like an average, but it's an average in which the zeros count as negative and the poles count as positive. But notice that since poles and zeros always show up in complex conjugate pairs, if you sum them up, the imaginary parts always cancel each other out. Okay? So you end up only needing to consider the real parts of the poles and the zeros. You can keep them around. If you want to keep the imaginary parts around, it's fine. They're just all going to cancel. So, and I guess maybe it's good to keep them around because if they don't cancel, then something's messed up. Good. With n being defined, capital N being defined as the difference between the number of poles and the number of zeros, the number of asymptotes is the absolute value of n. Usually it's going to be positive. Each is a ray that originates at sigma A, and all that remains undetermined is the angle of each ray, which can be shown to be as follows for all integers m. So our theta m, the angles of the asymptotes, are 2m plus 1 pi divided by np minus nz. Great. Note that these repeat every n consecutive values of sigma n, or of theta m. In other words, so if you've got 5 asymptotes and you compute 5 angles, you can stop because they're just going to start repeating themselves. They're just going to wrap around and repeat themselves. So you only need to compute as many angles as you have asymptotes. Okay, every root locus with positive gain will satisfy the rules above. They will help us construct sketches with the following procedure. Okay, so those rules are the only rules we're going to consider. There are other rules that you can consider that to refine your sketch, and they'll be in the Nice textbook if you so desire. I don't think it's particularly useful to get a lot more detailed than this, though. Okay, so this procedure is using this RL numbering. So root locus procedure step 1, RL1. Sketch the open loop poles and zeros. So since the root locus starts at open loop poles and ends at open loop zeros, it's a good place to start, right? It's a good place to start our sketch. We know our starting and ending points. 2, sketch real axis locus in accordance with rule 4. So this is a nice win. Let's get this out of the way quickly. Let's just like walk down the real axis, no locus, locus, no locus, locus, etc., and we'll go from there. Rule 3, or not rule 3, but step 3. If applicable, determine poles or zeros at infinity and draw asymptotes. So if we've got more poles than zeros, which is common, then we're going to have zeros at infinity, and we need to find out what the real axis intercept, sigma A, is going to be, and then what the angles of those asymptotes are going to be, the theta m equation. So then we sketch the asymptotes, and then finally we finish the root locus sketch respecting all rules. So usually we can come up with a nice qualitatively accurate sketch at that point, where you say, okay, I need things to be symmetric. I'm pretty sure that this pole goes to this asymptote. I'm pretty sure this pole goes to this zero, etc. So at that point you start doing your sketch, and it's, qualitatively accurate is the key there. That's what you're looking for. Okay, so those are the rules, and the only way you can get good at this is by doing some examples or practicing. So let's start out with a pretty easy one. Let's sketch the root locus for this transfer function. So we've got it's important to note, although it's implied, this is the open loop transfer function. So what is our first step? Well, first we need to draw some axes, right? So let's draw some axes. Okay. And we've got, let's figure out what are our poles. What poles do we have?
-3, -5.
-3 and -5, those are our poles. And our zeros?
-1.
-1. So they're all real, so they're all going to be on the real axis, right? This is our real axis, imaginary axis. And we're going to have to go back to here to -5, so let's say 1, 2, 3, 4. Ooh, kind of got big, didn't it? 5. And we'll draw in our poles and our zeros first, because that is our first step. Oh, where did I go? There we go. Sketch the open loop poles and zeros. That's our first step in the procedure. So let's go ahead and do that. So we've got a pole at -3. We've got a pole at -5. We've got a zero at -1. So that's pretty easy. Okay, step 2 in the procedure. Sketch the real axis locus in accordance with rule 4. So we start to the right of any of the zeros and poles. No locus. We march leftward till we hit the first zero or pole, and after which we have locus on the real axis. So there's locus here. No locus, again, toggles off. Then again, locus there. Okay. So now we've got our real axis done. And we see that one of our poles goes to this 0, and the other pole goes off to infinity. And like we didn't even compute the asymptote. We're kind of already done, though. But let's go ahead and double check that we're done. Nice. Nice little weed whacker. Okay, so now we want to know, we've got number of poles minus the number of zeros being equal to 2 minus 1, which is just 1, right? So we've got 1, 0 at infinity. Okay, so to compute what the angles are going to be, or to compute what the real axis intercept for that one asymptote is going to be, we say, okay, sigma A equals, we have the sum of the poles minus the sum of the zeros. The poles here are -3 minus 5 minus -1, which is the 0, divided by 2 minus 1, or -7, right? So we're like out here. We'll just say right here, because I don't want to extend the green arrow more. So I'll draw an asymptote. Well, I'll draw the asymptote stuff in purple. So like it's like out here. There's our sigma A. Now we need to do the angles. The angles, well actually the angle, right, there's only going to be one, is going to be at 2m plus 1 pi divided by 2 minus 1, or 2m plus 1 pi. So when m is 0, m is an integer, m is 0, we've got pi, and then we've got 3 pi, and then we've got 5 pi, etc. So this points at pi, angle of pi. This is theta. Well, it's theta, but I'll just say theta m. It's all of them, all the theta m's. And that's our asymptote. So we know that this pole, so this pole clearly goes to that 0. Okay, so now we're like, our last step is to finish the sketch. So this pole certainly goes to that 0. It's already done so on the real axis. This pole doesn't have a 0 to go to, a finite 0. It has to go to a 0 at infinity. The 0 at infinity is given as being negative infinity on the real axis. We just head out at pi, angle of pi, and that's exactly what our real axis rule already gave us. So it's done. Yes?
How do we know it's negative infinity and not positive infinity?
It's because the angle came out to be pi plus or minus 2 pi m.
So what would we have? Is there a way that you can get positive infinity, or does it not happen?
Let's see. It does happen, but it only happens once you get up to, I think, 4. I think if you have 4, might even be more. I think 4 zeros at infinity, you end up with a X pattern. I don't know. There might be one where you end up with 1 going to positive infinity. But the angle is what gives it away. It's an angle pi. Angle pi is always going to be pointed to negative infinity in real. So if you ever got 0 as an angle, which now that I'm looking at that formula, doesn't seem possible.
You'd have to have, because the 2 minus 1 is 2, that's from the NP minus NZ, right?
Yeah.
So you'd have to get like a half down there. Right?
Yeah, but they're always integers, subtracting. So
So you'd have to get like 2 minus 4. Or,
yeah.
so that's what,
If you ended up, yeah. I don't know. It does seem like it might be impossible to get one that goes to 0. I don't know. I'm looking at that. I feel like it's I think it's impossible because you're always going to be multiplying. You're always going to have this addition of pi over something. And that something is always going to be an integer. So m can be 0, can be 1, but this is just 2 pi. Yeah. Well, no. This can be a fraction too. Yeah, I don't know. I'm not sure. I've never thought about it that much. I mean, usually you end up with 4 asymptotes as like the max that you ever get. So I've not seen one with more. You could do it. It could be contrived. Okay, any questions on that example though?
just to draw the arrow on the,
On this guy?
no, on the,
Oh, on the asymptote?
is there an arrow on the green one on the right?
Yes.
Is there,
Oh, it's good to draw an arrow, but it's not required. So it's good to know, you know that it's originating at the open loop pole and going to the open loop 0. So that is the direction it goes. And in fact, let's actually sit here and interpret this for just a moment. We've got a controller that's just a gain, right? And if we set that gain to 0, our controller has closed loop poles at the open loop poles. As you increase the gain, we're going to move away, so like maybe that pole is over here now, maybe this pole is over here now, from those open loop poles. You have different open, and then you have different closed loop poles, okay? And as you continue to increase the gain, you can get all these different behaviors that having closed loop poles at these different locations are going to give you. In this case, if you increase the gain to infinity, will the system ever go unstable?
No.
No, because this pole is going to stop here at this 0, which is still stable. It's in the left half plane. And this pole is going to go off to negative infinity, which is still in the left half plane, so you're just going to have stability the entire time. Are you ever going to be able to have any overshoot? Any non-zero damping? Or sorry, any underdamping? Or is it always going to be overdamped? It's always going to be overdamped, right? Because you can never, in order to have underdamped, you have to be able to leave the real axis with your poles. These poles are never going to leave the real axis, so it'll always be overdamped. Your step responses will always look like exponential decays or sums of exponential decays. They'll never look like this with sinusoidal components in them. So you're never going to have any overshoot in this system, even if you keep increasing the gain. So that brings up, how do you change what the root locus is? I mean, the root locus is like, here's all the possible things you can do with this if you just have a gain controller. Well, soon enough, we're going to actually want to use controllers to get performance other than what's just on the root locus. We want to move that root locus around itself. So we're going to get there. But for now, we're just stuck with the root locus that is, and we have to just say, we can just change the gain and get different things to happen. All right. So let's go on to the other more involved example. So the other more involved example has got how many zeros?
3.
Zeros, no zero. So I switched it on you guys. So none that are finite. Yeah, I was so sneaky. Poles, there are 2 from this and 1 from that, so there are 3 total. And
There's 1 real and 2 imaginary.
yeah, these 2 are imaginary, and they turn out, so if you use the quadratic formula, set that equal to 0, you're going to find out that they show up at -1 plus or minus j1. So those are our 3 poles. So NP minus NZ equals 3 minus 0, there are no zeros, equals 3. So there are 3 asymptotes. And let's recognize that, and then we'll come back to this and compute the asymptotes. But let's get start out with our win. I like starting out with our win here, where we've got our real and imaginary axes, and we'll put in our open loop. So the first step in the procedure is to put in our open loop poles and zeros. So we've got a real pole at -5, and then we've got -1 plus or minus j1. So we've got a real one out here, and then we've got a couple complex ones here. And there are no finite zeros, so we're done with that. We can do our nice real axis rule, right? Our real axis process, where we start out rightward of any of the poles and zeros, no locus, move leftwards. These ones that are off axis don't count for this, just ones on axis. Move leftward, leftward, leftward. And then we hit this guy, and we got locus, okay? And it doesn't have any other zeros, so that one must go off to -infinity. So we're guessing that's going to be one of our asymptotes. Is going to go off that direction too. But we need 2 other asymptotes. And so let's go ahead and compute where the real axis, and I'll switch over. I'll do the asymptotes in purple. The real axis intercept of the asymptotes is going to be -5, the sum of the poles, so -5 minus 1 minus 1. So these are all, I just used the real part, right? Because I could have done -1 plus j1 and -1 minus j1, and then the 2 imaginary parts would have canceled. And then there are no zeros, so you could say -0 divided by 3 minus 0, np minus nz. So we get -7/3, which is like -2 1/3. So we're like in here somewhere. And the asymptote, so this is the place that the asymptotes all meet, is right here. Now we need to compute their angles. So the angles are theta m. They are 2m plus 1 pi divided by 3 minus 0, or 2m plus 1 pi over 3, where m is an integer. If we set m to 0, we get pi over 3, right? So pi over 3 is like 60 degrees. So we'll do something like that. Then if you plug in m equals 1, you get 3 pi over 3, or pi, which is just this direction, right? And finally, we get plug in m equals 2. We get 5 pi over 3, which is like -60 degrees. Okay, so those are our asymptotes. Clearly, this pole is going to go to that asymptote, right? It's already going there. Now, so the rest of it's just figuring out where these other two poles go to. So this pole is going to go to one of these two asymptotes, and this pole is going to go to one of these two. Usually they go to the asymptote they're closest to. There's a little bit of ambiguity here, but most of the time we don't need to worry about too much of this ambiguity, so we can fill in the rest of our root locus. Most of the time it's pretty clear. And they go like that. Symmetrically, right? They have to do, everything that they do is got to be symmetric about the real axis. So they do that. Now, let's, for just a moment, interpret these results. We have our root locus. It's done. What does this say if you keep increasing the gain? What happens?
It will eventually become unstable.
Yeah, it's going to go unstable, right? These poles are going to come up and they're going to cross over the imaginary axis and become right half-plane poles. So you can't just keep increasing your gain forever. You're going to have a closed loop system that's unstable. And this actually happens quite a bit. So you got to watch out for this. And another thing you could learn, qualitatively from this. So that's one thing we can learn qualitatively, that eventually, if you keep increasing the gain, it's going to go unstable. The second thing we could learn is that there's no way to make this system be anything overdamped. It can never be overdamped because you've got these off-axis poles, and they never come back to the axis. So if you keep increasing the gain, you're going to get what amounts to being more and more oscillation, more and more overshoot, less and less damping is going to happen as you increase the gain. So if you wanted to make this system have less damping or less overshoot than it does in open loop, you're screwed. You can't do it with just a gain, which is another sort of way of thinking about how we really want to be able to move this root locus around. For now, we're stuck with the root locus, just with the gain controller, but eventually we're going to do different types. So we'll start out with gain controllers, though. Okay, any questions on root locus? Okay. This is our big tool that we're going to use for doing design, so hopefully you guys have a pretty good grasp on it. All right. I'll see you guys Wednesday in a week. It's crazy.